Good afternoon, everybody. Thanks so much for joining us for another session of EI Live K-12. My name is Cassie, and I oversee educational and outreach activities at the Earth Institute. For those of you who are joining us for the first time and are not familiar with the Earth Institute, we are based at Columbia University, and our core mission is to foster a greater understanding of the science behind climate change and sustainability and what we as global citizens can do. So experts that make up the Earth Institute are actually quite interdisciplinary and diverse, and include economists, business and policy experts, public health experts, and of course, earth and environmental scientists. The Institute is actually made up of more than 24 or so research centers and several hundred people who actually collaborate across many different departments and disciplines at Columbia. So we're hoping that through these EI Live K-12 sessions, you'll get a better understanding for what our experts do. And we're going to have weekly sessions in this time slot, mostly in this time slot. There are a few that are not on Thursdays, but we're going to be having these sessions weekly until the end of June. So if you'd like any information about the upcoming sessions, please do not hesitate to contact me directly. So today we're really lucky to have Nichole Anest joining us from the Core Repository at Lamont-Doherty Earth Observatory, which is actually the largest research entity of the Earth Institute. And Nichole is the curator of the Core Repository, and she's going to be speaking to us about sediment cores and just what's in all that mud and why all that information is so important to our scientists. And I'm really hoping that we have some mud enthusiasts on the session today. So Nichole is going to do a presentation and do a quick demo as well. She's going to be switching between devices, so we'll make sure we
bear with me.
Exactly. So we'll all be very patient, and she's going to leave time at the end for Q&A. If you do have questions that pop up during her presentation, feel free to just use the Q&A box, pop that question in there. And then we're also going to have a colleague of ours from NASA's Goddard Institute of Space Studies also join us, and just to share a little bit of a couple of NASA resources that are also available related to sediment cores. So Nichole, whenever you're ready, take it away.
Okay. Hi, everybody. I'm going to share my screen right now. We're going to start with a lovely PowerPoint. Okay, there we go. All right. So my name is Nichole Anest. I am the curator here at the Lamont-Doherty Core Repository. You can see there's our website and a giant map. This map actually is hanging in our hallway. It's about 10 feet wide and 7 feet high. And on it, you can kind of see all these little dots around the oceans, right? There's some orange and yellow and red dots. If I can share something else with you, here is that map on the web, and we'll zoom in real close down here. And so you can see those dots in higher details. Feel free to go to the website yourself, use that link. So what do we have here? We have a lot of dots around the oceans. Each one of those dots represents one of the samples in our collection. Our samples consist of tubes of mud, right? And so I'll get to that a little bit. But you can see on the map, especially in the Pacific Ocean over here, that a lot of these dots are in straight lines. And that's because our founder, Dr. Maurice Ewing, told the ships, and I'll zoom in down here so you can see what the different colored dots actually mean, told our ships, first the Vima and the Conrad, that they had to collect at least one core every day while they were out at sea. And they were out at sea almost year round for nearly 30 years, right? So the Vima and the Conrad collectively went from 53 to 88, so over 30 years. So that is why we have one of the world's largest collections of this kind of mud, of these samples. Yeah, so we have this map. We have almost 20,000. We have over 20,000 samples of mud from the bottom of the oceans and all over the world. We're the only repository that has a global collection like this. So how do we get all of this mud? Well, we take a long tube, empty tube. They can be anywhere from 10 feet long to 160 feet long. And that gets lowered into the mud at the bottom of the ocean. There's up to a ton of weight at the top of the coring barrel. And that's all that pushes that barrel into the mud. The full barrel of mud then gets pulled back up to the ship. Now you can see here, right? Mud gets laid down, right? Oldest mud is at the bottom, newest mud is at the top. Like when you take off your clothes at the end of the day and throw them into the hamper, right? The clothes from Monday are at the bottom and the clothes from Friday are at the top of that hamper. It's the same concept, right? Stratigraphy, stratigraphic layers of mud. So because the mud is laid down like that, and we know that, the deeper into the mud we go, the further back in time we are actually going. And the mud at the bottom of the oceans, in the deepest parts of the ocean, it accumulates or it builds up at a very slow rate of only about 2 to 3 centimeters. So that's just about an inch of mud, right, every 1,000 years. It's very, very slow. As you get closer to the continents, right, to like where the beaches are, its sedimentation rates, right, the rate at which that mud builds up is a lot higher because you have a lot of stuff being washed into the oceans from the continents, from the land. So how do we actually use all this mud to do anything with it? Well, first, let me show you a series of pictures here. This is an actual core being pulled onto a ship. It's being pulled up from the bottom of the ocean off the coast of Portugal. This cruise took place in 2004, and we went from Portugal south, just past the northwest coast of Africa. But you can see the people, right? They're wrangling. This is a short core. It's only a 10-foot pipe. But they had to wrangle it because the seas were a little bit rough. But then it gets pulled onto the deck and cut down into sections, right? Maybe like 5-foot long sections. So that tube would have gotten cut in half. And then I'll tell you how we get the mud out of it in a couple of seconds. But first, let me tell you about basically very broadly the 2 different types of sediments that we see in the oceans, right? So there are many different types of mud. You can call it dirt, you can call it soil, loam, sand, clay, right? They're all types of sediments, right? So our tubes of mud, which are called sediment cores, can contain little bits of rock or mineral grains. They can contain volcanic ash, clays, and tiny shells of different types of plankton. And plankton, for those of you who might not know, right, they're tiny plants and animals that float or swim throughout the world's oceans. You can actually find phytoplankton, the plant type of plankton, in little puddles, in ponds, rivers, lakes. The zooplankton, the little animals, are more concentrated in the oceans, but they can be found in fresh water as well. So when we have little bits of rock, right, little mineral grains, we call that terrigenous because it's come from on land. And when we have little types of shells that make up most of our mud, we call that biogenous because of, bio is biology, is life. So here is an example of an unsplit sediment core. So the sediment cores come up as whole round tubes, and then they get cut down the middle lengthwise. So on the left is an unsplit sediment core from Long Island Sound. It has a clear liner, so you can see a little bit of a color change in the mud through the barrel. And on the right is that same core once it was split in half down the middle. So we split it in half down the middle, and then we have two mirror images. Two mirror images of that core. So this is the mud that was inside of that pipe. And you can see that it has some little white specks. Those are shells, right? So we would call this biogenous, but it's also mostly made up of sand, and sand is little mineral grains, little pieces of broken up rock. So it's both terrigenous and biogenous. But you can clearly see lots of layers. So lots of stuff was happening in Long Island Sound over the period of time that this core represents, which is probably not that long amount of time because it's in Long Island Sound, it's surrounded by land, and especially after major storm events like Hurricanes Irene and Sandy, you get a lot of mud and other stuff washing into such a basin. So the sedimentation rate is going to be pretty high. What is that? Oh. Sorry, there's a bit of a delay with my keyboard. So now I'm going to switch to a short video, or as part of a video, of a virtual tour of the repository that we did for open house this year. Oops. And again, bear with me, I have to go to that, and then I have to go here, and then I have to go here. And share it. Okay. So I'm going to play a little bit of this video. The full video, the link is in the PowerPoint presentation. And I'll go back to that screen in a little bit so you have a chance to see get the link. Hopefully the volume is up all the way on the video, so hopefully you can hear this okay. So for open house, every year we normally the campus is open every October, 1 week, 1 day in October. But because of the current pandemic, obviously we were not able to do that this past October. So here's a short bit of a virtual tour we did for open house.
So Nichole, we can't hear the sound on the video too well, but you can absolutely, I think the video itself is coming across really clearly. So if you just want to narrate a bit over it, and then I can share the link with everybody in the chat box.
Oh, okay, okay. Yeah. So
You've also done this
I'll mute it on my end because.
Okay. Yeah.
So what I'm showing you here are the storage trays for all of our mud, our sediment cores. And the names on there correspond to the cores in the tray. The V is for the ship name, the VIMA. It's the 17th cruise and the 26th core, let's say. And each sediment core automatically has 2 trays because it's split in half. But a lot of them, depending on how long they are, can have many, many more trays. These trays are 8 feet long, as you can see from the side. Our longest core is 33 meters long, so that's almost 100 feet. So it would occupy many of these trays. The second line of text on the trays is the depth of the section of core in the tray in centimeters. Whoa. But yeah, you can see the mud in these trays is very dry because it was taken into like the 1960s through 1980s. So the mud in these trays is all dried out. We do now have a walk-in refrigerator though, that I will show you another part of this video in a little bit. But you can see there the mud is different colors. And here we have a set of display cores that are out in the lab at all times, showing you many different things. Like you can see the one on the left versus the one on the right look very different. The one on the left, that orangey one, is composed almost entirely of tiny plankton shells, pteropods, and forams, which I'll show you later. And the core next to it, the gray one, right, that's all pumice. So it's volcanic in origin. This core, that's styrofoam that we put in the core to maintain the integrity of the core after we sample it. But you can see that it's tan, but right there, what I'm pointing out, that gray band is actually ash from the Mount Vesuvius eruption that buried the city of Pompeii hundreds of years ago. And the core here with the stripes, each one of those light colored stripes is a layer of diatom shells. Diatoms are phytoplankton, and we'll look at them in a little bit as well. But that was those are annual bands of diatoms. They bloom in the spring because they're a plant, they're an algae, and then they die off and their shells rain to the seafloor in the winters. And then where those stripes stop is the last ice age. And now these two cores are here to demonstrate differences in sedimentation rates, how quickly mud accumulates. The one on the bottom, that's all sandy with all the rocks in the bottom of it. Oh, I missed the part there. Sorry, I'm going back again. All right, I'll stop it here. The one on the bottom with the rocks, that's an 8-foot tray. These are the bottoms of the cores. The top would be to the left. The one with all the rocks was a massive underwater landslide caused by an earthquake. So an 8-foot length of sediment, of a sediment core, was laid down in a matter of days, right? Hours for those big rocks to fall out, and then a few days to weeks for the finer sands and clays to rain down to the seafloor from the landslide. The core at the top of the screen where it's black, right? The mud at the bottom there is 120 million years old. So the same amount of material as far as, the length of the core, but it was a much slower accumulation of muds through time. And that core in particular, you'll see it goes from being black down there, and then it becomes white and chalky, and then it becomes tan, going towards the left, going from right to left. And those changes in color represent actually what happens when sea level changed in the area that this core was being deposited. The black mud is actually, it's all organic matter. So like plants and bits of plants that fell into the ocean and then stayed there. They didn't get decomposed very much, but it's very rich in organic material, the black mud. The white mud, right, the white mud there is actually chalk, which is made up of the shells of some of the tiny plankton that we'll be looking at in a little bit. And then towards the far left of the screen where the mud is tan, is because sea level rose a little bit higher. So going from right to left, to the right, we're at the bottom of the core, we're at 120 million years. Going to the left, we're coming forward in time. So we're getting closer to the recent time. Sea level was rising. So all of the forams, sorry, we haven't gotten to forams yet, but the plankton shells that make up that chalk, they were diluted by more material coming in from land. So we have a time series in this core right here of sea level changing through time. So as we go, we're getting closer to recent time now. All right, and that's about it for the video. So I'm going to once again stop sharing. Oops, I didn't do that. And go back to sharing the PowerPoint. Make sure I'm not opening both places. All right. So that's the link for the full video. Like you might have seen, it's about a half an hour long. But we can share that with anyone who's interested later. So why do we want all this mud from all around the world? And why have we been collecting it since 1948? First off, the one major thing we find in mud at the bottom of the ocean is plankton shells, right? Plankton of various species have been around for hundreds of millions of years. A lot of them form shells or leave behind other hard parts that can become microfossils. So the biggest ones currently, they're about the size of an average grain of sand, right? So they're very small. But depending on the type of microfossil we find, like the species, not just whether it's a zooplankton or a phytoplankton, so a plant or an animal, but we can tell how deep the water was by what plankton we find, because some species like to live at the bottom of the water, some species like to live at the top of the water, some species like to live at various depths within the water column. Some species prefer hot water. Some species like cold water. So we can tell a lot of things just by the shells, the tiny microfossils that we find in the mud. So first we have diatoms, right? They're a phytoplankton. They're a type of algae. They're bio, right? Bio meaning biology. Biosiliceous because their shells are made of silica. And they come in various shapes and sizes. In the lower right corner, you can see a bunch, they look like little needles or hairs. They can be fibrous. The majority of them are round, and they're almost always flat or disc-like, right? Even if they're not round, they're typically flat. And you can look up diatoms on the web. A lot of people, like that lower left picture I have here, quite a few people have become like microscope artists, and they lay out diatoms and other types of plankton shells in artistic patterns and things. It can be quite beautiful. So a second type of plankton, another phytoplankton, also siliceous, so silica based, are radiolaria. And they are all different shapes and sizes, as you can see in these beautiful pictures, but they're all spiky, right? They all have these little spikes coming out of them. Whether they're, even after they die, their shells are still spiky. So the middle picture is actually a living radiolaria with parts of its membrane sticking out into the ocean through holes in the shell, trying to catch anything that's even smaller than it is to eat. So they're not just photosynthetic, so plants use the sun to make energy, sunlight, but they can also catch other types of algae even and incorporate them into themselves. And the third type of plankton we have are called foraminifera, forams for short. These are a zooplankton. They're calcareous, so they're made out of calcium carbonate, which is the substance that makes up chalk. So foraminifera and another species or another group of plankton called caucoliths make up all the chalk in the world. So once their shells are compressed through time at the bottom of the ocean, they get smushed into a hard clay-like white substance that we know as chalk. In the bottom right corner is a picture of a living foram. Looks very similar to that radiolaria, right? So it's just all parts of its membrane are sticking through all the tiny little holes in the shells. And so we can also find mineral grains. They're usually found closer to the continents, to the beaches. They don't travel out into the deepest parts of the oceans because there isn't enough energy in the water to move them around. You have waves at the beach, excuse me, and those waves, right, that's a lot of energy close to the shore. But that energy doesn't extend out into the deepest parts of the ocean, at least not at depth. You can have waves at the surface, but those waves don't, the energy isn't consistent all the way down to the ocean floor. So you get sorting of grains by size, basically. So you have beach sand, which will typically be all of one size in any given area. And then as you go farther and farther out from the beach into the water, the grains will get smaller and smaller. If you were able to walk along the bottom of the ocean, you would see that the grain sizes get very small as you continue out. Except in various places where icebergs have been. So icebergs, they're scraping up, ice sheets, I should say, scrape up all the rocks and dirt on land as they travel on the continents. But then once they break off from the ice sheet and float out to sea, they will start melting. As they melt, all those rocks and bits of ground that they picked up fall to the bottom of the ocean floor. So we can actually trace the paths of icebergs through the oceans based on the rocks that they drop along the way. Those little rocks and bits of debris that they drop is called ice rafted debris. So again, mineral grains can tell us similar things to what different types of plankton shells tell us. Basically how deep the water is and how hot or cold it is, because the colder it is, the colder the water is, the longer the icebergs will survive and they won't melt as quickly. So they'll travel much, much farther. So here's an example of a core, a sediment core from the North Atlantic Ocean. There are, you can see many layers in there. You can see light layers, light bands, right? Darker bands. And these in between, these orangey colors. The orange color, if anyone can guess, is from iron. Iron in the grains and the minerals in the mud that's oxidized. So it's basically rusted, right? Rusted grains. These darker layers, though, the blacker ones, that's actually a layer of ice rafted debris from where an iceberg was melting and dropped a whole bunch of little rocks. This core, the area it was taken from, is in the path of where multiple icebergs, even today, come out of the Arctic Ocean and travel into the Atlantic Ocean. This core from Haiti, right, the island of Haiti, it was taken right after the last major earthquake there in the 2000s. And you can see it has, again, we have rusted mud, right here. It's reddish orange, but it has these layers of sand. Each one of these layers, sand layers, was laid down during an earthquake, right? So you get an earthquake in a small bay, and all the mud and stuff from the sides of that bay start collapsing into the basin. The bigger grains, the sand grains, fall out first, filter through the water column and land at the bottom of the seafloor first because they're bigger and heavier. And all the smaller things, you know, fall out afterwards. So each one of these sequences, a sand layer and then all the mud on top of it, was one earthquake. And then you have a sand layer and all the mud on top of that came from another one, and so on and so forth. Where you have a big gap between the sand layers, that's because there was just regular, everyday sedimentation of grains falling through the water without an earthquake causing it. I see a couple of questions. How do I know what the patterns mean? Because people have been studying these sediments and muds at the bottom of the ocean and on land for centuries, actually. So it's been a long time. It's just been a lot of experimentation to figure out how to identify specific types of layering in the mud. So I know what this means because so many people before me figured it out. But basically, you can create like you can get like a clear plastic tube, a piece of PVC pipe or something, put a bunch of mud in it of different sizes, like put some pebbles, some sand, some clay in there. Fill it like 3/4 of the way with water, you have to cap both ends, right? And then just shake it up and then turn it on one end so it's standing up straight and see what happens. See what lands at the bottom first. You don't even have to use rocks and clay and mud. You could use, you could throw anything in there that your parents don't mind getting wet. Okay. I click the button. So now I'm going to actually wash some mud. That's the first thing anyone ever does with some of the samples that we send them. So from those pictures of the cores that you saw, you can imagine, right? So it's soft mud, like clay that you would play with, or pottery clay or something. You just take a sampling tool like this one. It's just like got a scoopy end on one side, and you would dig that into the mud and just scoop it out, right? That's how you would sample those kind of sediments. The next thing you do is wash it. Basically, we put it through a 63 micron sieve. So a micron is 1,000th of a millimeter. So here at the bottom right corner is the sieve I'll be using. All right, here's a sieve, and you can see through it because it's a mesh, like a screen door. It's just that the holes in it are very, very, very tiny, very tiny. And I'll show it to you under the microscope once we have some washed mud in it in a few minutes. But so for this exercise, we're going to use a soft brush, the sieve, a bucket to collect all of the water and the mud that comes out. If you have a sieve at home and you want to try sieving mud or anything else, do it into a bucket, because whatever comes out of this sieve will clog your drains. So don't do that. Here in our labs, we have special things called sediment traps in our plumbing, so that any mud that goes down the drain falls into a trap and doesn't clog up the pipes. But so if you're going to try sieving it all at home, do it into something that can catch all that mud that you can then just throw outside or someplace, and don't clog up your parents' drains. And then we have a wash bottle, right? You could use a cup or whatever else. But these are they're just bottles full of water, and when you squeeze them, water comes out of them. So I'm going to attempt switching to my phone camera now so that you can look into the sieve as I put a sample into it and wash it for you. So let's see if I remember how to do this.
Okay, so Nichole, before you do that, stop sharing, and then we can go to your phone.
Oh, there's a question here. What do the planktons have to do with the mud? I'm sorry. So all of these plankton are living in the oceans all over the place. Sorry, I'm trying to set up my phone at the same time. The plankton, I'll put the sieve here so that it's not so distracting. The plankton are living in the ocean water. they're floating or swimming. They're just hanging out, doing their thing. And when they die, their shells rain to the ocean floor. And that process has been going on for hundreds of millions of years. So the oldest mud at the bottom of the oceans is a few 100 million years old. So even though the planet is 4 billion years old, thereabouts, the mud isn't as old. But that's how the plankton shells get there. Is they're living in the oceans, and when they die, their shells rain to the ocean floor and build up over time. So here I'm going to, I just noticed the time, we're almost out of time. I had a piece of, this is a piece of a,
It's okay. I'm spotlighting your phone video
Oh,
so we
okay.
can see your the sieve much clearer.
Okay.
Yeah.
So I have a small core over here, and this is a piece of that core. It's hard, it's chalky, but in the, because to save time, I put a chunk of that mud into this beaker with some water a couple of hours ago, just so it would break down into its sediment faster, in case we ran out of time. So I'm just going to pour this. This is just mud, right, in water, into my beaker here, into my sieve. I'm going to get all of it out with my wash bottle. And then I'm just going to start brushing it and washing it at the same time. Brush it around so it all goes through. You can see you can kind of see there's water in there, but trust me, it's going through. Hopefully soon we'll be able to do these in person again. That way you all can wash your own mud. Now you can see maybe a lot of it, there's a little too much light actually, so it's hard to see. Everything's kind of washed out, but there is, I assure you, some grains in there. We just swirl it around. I'm not pressing hard or anything, just gently washing it. And hopefully you can see, right, that there's a collection of sediments in the middle of my sieve. You can see there's a lot of muddy water in the beaker. So I'm going to just dry it a little bit, the mud, so it'll be easier to see under the microscope with less water. Let's see, there's another question. All right. So I see this question about coral skeletons are similar. Coral skeletons can be similar to my mud layers, yes, because they actually have annual growth bands, some corals. So they're actually a lot like tree rings. So tree rings are annual. Cassie, yeah, thank you. And so can corals. Corals grow with annual growth bands. So we can get, like from my mud, because sedimentation rates, the rate at which mud is laid down, is so slow, it's hard to see back to to get any annual data. We can get data out of the mud, say in some places for like the past 1,000 years. But from corals and tree rings, you can get data from just like last year or like the past 10 years, right? It's a lot more, specific and concise in time. Okay, so now I'm going to share my screen again. Wait, let me check that question that just came in real quick. How do I know when to do everything? I don't. I wish I did know when to do everything. All right, let's share my Dino capture. Share it. All right, I'm going to plug in. I have a microscope that has a USB plug on it, so that I can show you what these grains look like. So there we have, it's still wet. That's why it looks so a little funky, like it's in gel or something. But this is the mud that I just washed. And you can see some shells, right? I'll try moving it a lot slower than I just did. It's still very wet, but these whiter things are shells, right? These little plankton shells. And in between them, all these clear grains are little sand grains. So quartz is in there. Let's see what else we did. So this core too, ooh, this thing right here, this big flake looking thing, that's actually mica. Mica is another kind of mineral that we can find. But that tells me that this core was actually close to land, because it's more terrigenous, right? There's more sand grains than there are shells. I'm going to try and dry it out a little bit more and see if that helps. But really, so sediment cores can just tell us the history of a place in the oceans based on what we find there. They can tell us how Earth's climate has changed through time. Because we can tell how hot or cold it was based on the shells we get and things. And, oops, sorry, I'm distracted by your questions. But let me start that over again. Yeah, cores, so sediment cores can tell us a lot about Earth's history, Earth's climate history, right? We can go back over 120 million years. I have, our oldest mud is 130 million years old in this repository. And based on the types of shells we find, the types of plankton we find, the ratio or how much shells versus mineral grains, that kind of thing we find, the different types of mineral grains that we find, all of that together, all of the different data analyses we can do will give us a history of that, the area where we took the core, but can also give us a broader history of Earth's climate, because we can tell when, from the shells, right, when the oceans were warmer and when they were colder. And that we can extrapolate, or we can use as an example of what the Earth's larger global environment was doing at the time. So we know when the ice ages have come and gone based a lot on information we've gotten out of the mud at the bottom of the ocean. So that's a good question. So the mud at the bottom of the oceans is younger than what's on land because of plate tectonics. If you all know anything about plate tectonics, I'll just give you a little briefing. But plate tectonics is, right, the plates, the continents are moving around on the Earth. But in the oceans, you get, hold on, I'm going to stop sharing my microscope and share my PowerPoint again so I can go to the map. Let's move that out of the way. So you can kind of see here in the Pacific Ocean, right? The Western Pacific Ocean over by Japan, that dark line is actually a trench. That's where the ocean floor is going beneath the continents. So the ocean floor is constantly being recycled into the inner planet, into the mantle. So that's why the mud at the bottom of the ocean and the ocean floors themselves are younger than the continents, because they're constantly being recycled back into the Earth's mantle and remelted. And then all that magma comes up in the middle of, you can see it clearly in the Atlantic Ocean, the mid-ocean ridge down the middle of the Atlantic. So yeah, so technically, yes, the ocean floor is younger than the land. So I think I had barely just enough time to get all of that in.
No worries, Nichole. So I'm going to have you stay on for a few extra minutes. So thank you. First of all, that was awesome. I love watching the washing and the sieving every time, because it amazes me that what we can't see with our eyes, and then when you put it under a microscope, it's like, oh my gosh, there's so much there. So I think that's super great. Thank you. So I'm going to have Rosalba from NASA GIST come on. Nichole, if you want to stay on, but mute your microphone. And for those who are still here, if you do have any questions, any additional questions for Nichole about mud or anything that she talked about, feel free to use the Q&A box. And Nichole, you can take a look at that box and you can type your answer in there too. Yeah, so Rosalba, if you want to let us know what NASA resources there are related to this topic, that would be awesome.
Yes. Hi, Cassie. Thank you so much for the opportunity to share about some NASA resources. I'm trying to share my screen now. Some difficulties here. I don't know if you can see my screen now. Yeah, sorry about that. My machine is not behaving. So yes, my name is Rosalba, and I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies here in New York City. And I just want to quickly share about some resources that have to do with coring. The first one is Climate Kits. The second one is the Scientific Visualization Studio. And the third one is some animations about Mars Perseverance Rover, which may sound a little bit crazy, but I will tell you more about it in a little bit. So Climate Kits is a pretty fun website that offers articles, games. It has hands-on activities, videos, and more, like the name says, about climate. So there's a lot of information about greenhouse gases, oceans, rivers, lakes, and so on. So there's a specific section of this website that has information about what paleoclimatologists do and how they use tree cores and ice cores and lake and ocean sediments to study Earth's climate. So I do suggest for you to check this out. And again, check also the other games that have to do with climate on this fun website. The second resource is the Scientific Visualization Studio, or SBS. So the SBS works very closely with scientists to create visualizations and animations and other images so that we can understand better Earth science and space science. And so there is a specific video, and I'm going to send you on the chat, I'm going to put the links for these resources. So on this Scientific Visualization Studio, there is a specific video that I shared the link to that has some scientists working with ice cores. They're drilling and they're getting ice cores to study Greenland's ice sheet. They also go on to talk about another mission called Ice Bridge. But yes, I wanted to share about that video where you can see the scientists working on these ice cores as well. And then the third resource is the animations of the Mars Perseverance Rover. And so this is because just as we can study or find clues about Earth's past climate with core samples, that is something that the Mars Perseverance rover is going to try to do also for Mars. So something that makes this rover different to other Mars missions is precisely that this rover has a drill for coring samples from Martian rocks and soil. And so the animation that I sent you the link for on the chat will let you see how this drill works and how this rover is going to retrieve those samples. And so the idea is that the rover is going to save those samples in some specific locations on Mars, so that then a future mission will go to Mars to get the samples and bring them back to Earth so we can learn about Mars' past climate. I think that's very cool. And yeah, so that's what I have for you today. Thank you.
Great, awesome. Thank you, Rosalba. And I think all super relevant. I love the connections that you can do core samples, you know, from the bottom of the ocean to outer space. Yeah, so thanks again, Rosalba. So Nichole, so I see that we don't have any more questions. So for our viewers who are still on, thank you for hanging in there. If you do have any additional questions, type it in the Q&A box. Nichole, any last pieces of info you want to share with our viewers, which are made up of both students, teachers, parents. So yeah.
So we actually have pre-made slides of a lot of this mud that we give out to classrooms at no cost, no charge. So you can contact me if you want anything. I can also send you raw samples if you have sieves and you want to do washing activities on your own as well. Yep.
Okay.
Yeah, there were a few questions that I answered while.
Yeah, I saw that. Thank you so much. Yeah, and we'll definitely share links to that for everything that came up in our discussion. And one of our other educators at Lamont, Margie Turin, came up with this activity a couple years ago when we did World Science Festival, where you can essentially build your own sediment core out of snacks and items in your house or apartment. And we have that activity written up. And so I'm definitely going to share that with everyone.
I want to share a picture too. I forgot.
Oh, yeah, go for it. Yeah. And we'll share the activity. We'll post it on a page with this recording. And you can try and make your own sediment cores at home and learn about all the layers. And then the best part, you get to eat it afterwards.
And I'll show you when our second ship, the Robert Conrad, was finally retired, they made a core cake.
Oh my God!
The celebration.
I love
that thing with a cake, just layers of cake.
So great.
And I was looking online, right? Even if you just make a layer cake, you could then, core it, right? If you have a straw or some sort of tube, you can plunge it through that cake and pull it out, and you will see the layers of your cake. But yeah, a core cake as well. Awesome.
That's great. I love that. That's definitely something I want to try in the future. Did you eat the cake? Nathan asks if you ate the cake.
No, well, unfortunately, it was long before I started working here.
Okay.
So.
Right. Well, I'm sure there's a lot. I'm sure there's a lot of people who did eat the cake, though.
Yes, there were a lot of people there.
Sure. All right. Well, thank you so much, everyone, for tuning in, and for our presenters. Nichole, thank you so much for sharing a little bit of your work with us and what you do. Really appreciate it. And if you have any additional questions, let us know. Otherwise, hopefully we'll see you at a future EI Live K-12 session. Thank you again, everybody. Have a great afternoon, evening. Bye.